Welcome everyone. During this lecture we'll introduce the rotational motion with constant angular acceleration equations. We'll explore a rotational motion with constant angular acceleration application. We'll develop the relationships between rotational and one-dimensional motion. And we'll explore a multi-phase application involving rotational and one-dimensional motion. Let's introduce the rotational motion with constant angular acceleration equations. As it turns out, the rotational motion equations bear a strong resemblance to the one-dimensional motion equations that we developed earlier. To show this resemblance, we're going to introduce them alongside the one-dimensional motion counterparts. Using a table, we'll introduce the rotational equations on the left and the one-dimensional motion equations on the right. We'll start by introducing the equation x equals v0t plus 1/2 at squared. Its rotational counterpart looks like this. Delta theta equals omega 0t plus 1/2 alpha t squared. Let's note the similarities between these two equations. On the right-hand side, x represents linear displacement, whereas on the left-hand side, delta theta represents angular displacement. On the right, v0 represents initial linear velocity, whereas omega 0 represents the initial angular velocity. Finally, on the right, a represents linear acceleration, whereas alpha represents angular acceleration on the left-hand side. The next equation that I'd like to introduce is v equals v0 plus at. Now on the left-hand side, v is represented by omega. Rather than v0, we'll introduce omega 0 plus, rather than a, we'll introduce alpha times t. So that's our second equation. Our third equation on the right looks like this. V squared equals v0 squared plus 2ax. On the left-hand side, the counterpart equation looks like this. Omega squared equals omega 0 squared plus 2 alpha delta theta. So as you can see, the v's on the right are replaced by omegas on the left. Rather than a, we're replacing a with the first letter of the Greek alphabet, which is alpha, and x is being represented by delta theta on the left. One, of course, on the right being linear displacement, and the variable delta theta on the left represents angular displacement. The next equation is v bar equals v0 plus v divided by 2. On the left-hand side, the equation looks like this. Omega bar equals omega 0 plus omega divided by 2. The next equation is x equals v bar t on the right. Its counterpart on the left looks like this. Delta theta equals omega bar times t. Of course, v bar represents average linear velocity, and omega bar represents average angular velocity. The final equation looks like this. X equals v0 plus v over 2 times t. Its counterpart on the left looks like this. Delta theta equals omega 0 plus omega over 2 times t. We will now introduce an example that demonstrates the application of these equations. In this example, the angular velocity of a flywheel decreases uniformly from 1200 revolutions per minute to 500 revolutions per minute in 6 seconds. In part A, we need to determine the flywheel's angular acceleration. Let's begin by identifying the known quantities. The 1200 revolutions per minute refers to the flywheel's initial angular velocity. And of course, angular velocity is denoted by omega. And so omega 0 equals 1200, and revolutions per minute can be abbreviated as RPM. Unfortunately, RPM is not an appropriate SI unit. It needs to be converted to radians per second, and we will apply the conversion factor that we developed earlier that transforms RPM to radians per second. That conversion factor is 1 RPM equals 0.1047 radians per second. So the RPM disappears, and the result equals 125.6 radians per second. Likewise, the 500 revolutions per minute refers to the object's final angular velocity, which is denoted by omega. And so omega equals 500 RPM, and that also needs to be converted to radians per second, so we'll use the same conversion factor. 1 RPM equals 0.1047 radians per second, and the result equals 52.35 radians per second. Let's also note that the time is given as 6 seconds. We're now ready to pursue part A, which requires that we determine the flywheel's angular acceleration. So in part A, we would like to find, and the question now is, which variable represents angular acceleration? Well, if we look back to our rotational motion box, alpha represents angular acceleration. So we would like to find alpha. Let's take inventory of what we know. Once again, omega 0 is known, omega is known, and so is the time. Let's now look at the box and identify an equation that's going to work for us. Now, the first equation is not going to work because we don't have delta theta available to us. Delta theta refers to angular displacement, and that was not given. The second equation looks like it may work. We have omega 0, and the time was given. Therefore, this is the equation that we're going to use. And so omega equals omega 0 plus alpha t. Omega has a value of 52.35. Omega 0 has a value of 125.6 plus alpha, and the time was given as 6 seconds. We're going to subtract 125.6 from both sides. The result is negative 73.25 equals 6 alpha. And if we divide both sides by 6, alpha equals negative 12.21, and the units for alpha are radians per second squared. Note that we obtained a negative value for alpha, and that's because the flywheel is slowing down. And let's verify that observation. Again, in this problem, the flywheel's velocity decreases from 1200 to 500, so that confirms the negative acceleration that we found. In part B, we would like to determine the number of revolutions completed during this time. Now first, let's note that a revolution is not an appropriate SI unit. However, it is comparable to radians, which are an appropriate SI unit. And radians are the units used to represent angular displacement, which of course is represented by delta theta. So we're going to determine delta theta first in radians, and then we'll convert that result to revolutions. So in part B, we want to find the number of revs. And we'll make a note that we will find the angular displacement first. Once again, let's take inventory of what is known. Alpha is known, we just calculated it. And of course, omega 0, omega, and t are known as well. Let's refer to our rotational motion equations and explore the first one. Is this equation going to work for us? Well, we're looking for delta theta. Omega 0 is known. The time is known. We just calculated alpha. It appears that this equation is going to work. And so delta theta equals omega 0 t plus 1/2 alpha t squared. Omega 0 was given as 125.6. The time equals 6 seconds plus 1/2. The value for alpha was negative 12.21, and the time once again equals 6 seconds. If we enter these values into our calculator, the result equals 533.8 radians. We would like to determine the number of revolutions, though. And in order to do that, we're just going to convert the radians to revolutions. So the revolutions just equal 533.8 radians times, we know that one revolution amounts to 2 pi radians. The radians cancel, and the answer is 84.96 revs. And so the flywheel will rotate 84.96 times within that 6-second time frame. Let's take a look at part C. In part C, we would like to determine the additional amount of time required to bring the flywheel to rest. In order to determine this time, we'll first of all calculate the total time required to bring the flywheel to rest, and once we determine the total time, we'll subtract 6 seconds from that. Let's label this time as T additional. And we'll note that T additional just equals the total time of motion, which we'll call T total, minus the first 6 seconds. Now, in order to determine T additional, we're going to have to find T total first. Let's also note that since the flywheel comes to rest, its final angular velocity equals 0, and so omega equals 0 for part C. Let's now identify an equation that's going to solve for the total time. Can we use the first equation? Well, the answer is no, because we don't know the flywheel's angular displacement when it comes to rest. Let's take a look at the second equation. In the second equation, we do know the flywheel's final angular velocity in part C. It equals 0. We know the initial angular velocity. We know the angular acceleration, and we're trying to find the time. This is the equation that we're going to use. And so omega equals omega 0 plus alpha t is useful to us. Omega in part C, which is the wheel's final angular velocity, which is stated, equals 0. The initial angular velocity was given as 125.6. The angular acceleration was calculated as negative 12.21. And we need to find the time. Let's transfer this term to the left-hand side. It's negative on the right, and therefore it's going to become positive on the left. And so we obtain 12.21 t equals 125.6. We'll divide both sides by the 12.21, and the result equals 10.29 seconds. Now, this is the total time of motion, so we'll label it as T total. We need to find the additional time required to bring the flywheel to rest. As we noted earlier, T additional just equals T total minus 6. And so we have 10.29 minus 6 which equals 4.29 seconds. Now there's another way that we could have pursued part C, and let me show you an alternative approach. Part C again asked us to find the additional amount of time required to bring the flywheel to rest, and in order to find that time directly, we could have started the problem at the point when the flywheel reached an angular velocity of 500 revolutions per minute. Of course, it reaches that point after 6 seconds have elapsed within the problem. Now, if we're pursuing this approach, then the 500 revolutions per minute would have been labeled as the initial angular velocity. So this omega would have been labeled as omega 0, and the final angular velocity would have been 0 because the flywheel comes to rest. And if we pursued the problem in that fashion, then the result would have yielded the additional time directly. In fact, I would encourage you to try that approach and see if your solution turns out to equal 4.29 seconds. We will now introduce various relationships between the one-dimensional and rotational quantities. Starting with an equation that we're already familiar with. That equation is S equals R times delta theta. Now S refers to arc length as well as distance, and in one-dimensional motion we refer to distance or displacement as x and delta x. Therefore S is the same as x and delta x within the one-dimensional motion equations. And so we can represent this equation as delta x equals r delta theta. We're now going to divide both sides of this equation by delta t. And the result looks like this. Delta x over delta t equals r times delta theta over delta t. Now we are familiar with delta x over delta t. That relationship, of course, is the definition of velocity. And delta theta over delta t is the definition of angular velocity. Therefore, linear velocity is connected to angular velocity through the following relationship. V simply equals r times omega. Let's introduce the delta symbol in front of the left and right hand sides. If we do that, we obtain delta V equals R times delta omega. Once again, we're going to divide both sides by delta t. And the result looks like this. Delta V over delta t equals R times delta omega over delta t. On the left-hand side, delta V over delta t is simply the definition of linear acceleration. And delta omega over delta t on the right represents angular acceleration. And therefore, we have a relationship between linear acceleration and angular acceleration, which looks like this. A equals r times alpha. Now, this acceleration is known as linear or tangential acceleration. Later, we're going to talk about something called centripetal acceleration, and we need to distinguish between these two types of acceleration. So let's just note that r times alpha represents something called linear or tangential acceleration. So this acceleration is known as linear or tangential acceleration. we're going to label it as A sub t. Let's summarize these relationships within a chart. The first equation is S, which is the same as X, equals R times delta theta. The second equation is V equals R times omega, and the last equation is A tangential simply equals R times alpha. We will now introduce a two-phase example which demonstrates the application of the various relationships that we've discussed thus far. In this example, a turntable with a radius of 30 centimeters starts from rest and reaches a speed of 500 revolutions per minute in 8 seconds. At this time, the turntable's motor is turned off and the turntable comes to rest after completing 45 revolutions. In part A, we would like to determine the turntable's total time of motion. Now, before we begin, let's first of all note that this is a two-phase problem. The turntable starts from rest and reaches a speed of 500 revolutions per minute. That means that initially the turntable is speeding up. When the motor is turned off, the turntable eventually comes to rest. That means that the turntable is slowing down. And therefore it is experiencing two different accelerations, and that requires a multi-phase setup. And in this example we have specifically two phases that we have to address. Let's begin by identifying the known quantities. First of all, the radius is given as 30 centimeters, which needs to be converted to meters. Therefore, the radius equals 0.3 meters. Next, the angular velocity is noted as 500 revolutions per minute. And that, of course, is the final angular velocity. The turntable started from rest, and that means the initial angular velocity equals 0. Now, angular velocity is represented by omega. So, omega 0 is 0 in this problem. And the final angular velocity in the first phase equals 500 revolutions per minute, which of course can be abbreviated as RPM. As we stated earlier, RPM is not an appropriate unit, and therefore it must be converted through 1 RPM equals 0.1047 radians per second. Therefore, the final angular velocity in the first phase of the problem equals 52.35. Now, we also know that the turntable completes 45 revolutions before coming to rest in the second phase of the problem. 45 revolutions refers to the turntable's angular displacement. However, revolutions are not an appropriate unit to describe displacement. The revolutions must be converted to radians. Now, angular displacement is represented by delta theta. The value that's given is 45 revolutions, and we know that 1 revolution equals 2 pi radians. Therefore, delta theta in phase B equals 282.7 radians. We will now introduce a chart which separates the various quantities into their appropriate phases. Again, this is a two-phase problem, so we'll label the first phase as phase A, and this is the phase where the motor is on. and phase B will represent the period when we turned off the motor, when the motor's off. Now phase A begins when the turntable is at rest. Therefore, omega 0 in phase A equals 0. Also, the turntable reaches a speed of 500 revolutions per minute, which we converted to 52.35 radians per second, and that, of course, is the turntable's final angular velocity in phase A. And so omega equals 52.35 radians per second. The time for phase A equals 8 seconds. Now, from our experience with one-dimensional motion analysis, we know that the final velocity in one phase becomes the initial velocity in the next phase. So the final velocity in phase A equals 52.35. That becomes the initial velocity in phase B, and we're going to note that. So omega 0 in phase B equals 52.35 radians per second. Also, the angular displacement was given as 45 revolutions, and we converted that to 282.7 radians. So delta theta equals 282.7 radians. And the turntable comes to rest in phase B, therefore its final angular velocity equals 0. We're now ready to pursue Part A. Now in Part A, we're looking to determine the turntable's total time of motion. And in order to do so, we need to note that T total equals the time we spent in phase A plus the time that we're spending in phase B. Now, the time for phase A is already given, right? The time in phase A was given as 8 seconds, so therefore we only need to determine the time for phase B. So let's enter phase B. And let's also take inventory of what is known there. Again, we know the value of omega 0, delta theta, and omega, and we would like to determine the value for time. So let's take a look at the rotational motion equations. Is the first equation useful to us? Well, the answer is no, because we don't know the angular acceleration for either one of the phases. In the second equation, we also need to know angular acceleration in order to use it, so that's not useful to us. Angular acceleration appears in the third equation. The fourth equation does not contain time. The fifth equation does contain time, but we don't know the average angular velocity in phase B. The last equation is going to be useful because the angular displacement in phase B is known. We know the initial angular velocity, we know the final angular velocity, therefore we can determine time. So let's bring this equation into our analysis. So delta theta just equals omega 0 plus omega over 2 times t. That'll equal omega 0 in phase B was given as 52.35. Omega in phase B, as you recall, equals 0. And delta theta in phase B was given as 282.7. And so that results in 282.7 equals 52.35 plus 0 over 2 times t. On the right-hand side, we have 26.18 times time, and if we divide both sides by 26.18, the time equals 10.8 seconds. And of course, that's the time that the flywheel spends, or the turntable, I should say, spends in phase B. Therefore, T total just equals TA plus TB. TA in our chart is given as 8 seconds, and the time we spent in phase B equals 10.8 seconds. Therefore, T total equals 18.8 seconds. Let's take a look at Part B. In Part B, we would like to determine the total number of revolutions completed. Now, revolutions are an inappropriate unit. They do, however, represent angular displacement. And so the strategy is to find the angular displacement in radians first, and then convert the radians to revolutions. So again, in Part B, we want to find the total revolutions. And to do so, we're going to find the total angular displacement first. Now, angular displacement is represented by delta theta. And we can note that delta theta total equals the amount of angular displacement in phase A plus the amount of angular displacement in phase B. Now let's take a look at our chart. As you can see, delta theta in phase B is already known, so we could place a check mark on top of delta theta B. However, we will need to find the angular displacement in phase A. So, let's enter phase A, and we'll also take inventory of what we know in phase A and see if we can find an equation that solves for delta theta within phase A. So, in our chart, omega 0 is known, omega is known, and the time is known within phase A. Let's take a look at the equations. Is the first equation useful? Well, as we discussed earlier, the answer is no, because we don't have knowledge of the angular acceleration. Same goes for equation number 2. The angular acceleration is not known. In the third equation, again, we don't know the angular acceleration. In the fourth equation, there's no reference to angular displacement. In the fifth equation, there is a reference to angular displacement. However, we don't know the average angular velocity. We have one more chance here, and that's the sixth equation. Here's the angular displacement. Omega 0 is known in phase A. Omega is also known in phase A. And the time is 8 seconds in phase A. And so let's introduce this equation. Delta theta equals omega 0 plus omega over 2 times t. Omega 0 in phase A was 0. The final angular velocity in phase A is 52.35 over 2, and the time in phase A equals 8 seconds. Therefore, delta theta in phase A equals 209.4 radians. And let's note that this is delta theta in phase A. And so delta theta total equals delta theta in phase A plus delta theta in phase B. The values, of course, are 209.4 plus 282.7. And if we add those two values, we obtain delta theta total equals 492.1 radians. We can now convert the radians to revolutions very easily. So the total revolutions simply equal 492.1 radians, and we know that one revolution amounts to 2 pi radians. The radians cancel, and the total revolutions equal 78.32. In part C, we would like to determine the total distance traveled by a point on the turntable's rim. That distance can be determined through the relationship S equals R delta theta. Of course, S refers to distance or arc length, and so does X. And delta theta refers to the total angular displacement, which we just determined. So this is the equation that we're going to apply. Once again, S just equals R times delta theta. The radius was given as 30 centimeters, which was converted to 0.3 meters. And we just found the total angular displacement, and we have to enter the radian version into this equation, right? Revolutions are not appropriate. And so we'll enter 492.1. And as a result, the total distance equals 147.6 meters. In part D, we would like to determine the turntable's angular velocity at t equals 12 seconds. That's a little tricky. First of all, we have to determine the phase in which we are in when t equals 12 seconds. As you can see from our chart, phase A ends after 8 seconds. Therefore, at 12 seconds, the flywheel has entered phase B. Also, it's important to note that at 12 seconds, the time that the flywheel is spending within phase B equals 4 seconds, right? Because the first 8 seconds were spent in phase A. And so when we apply the time in phase B for this part, t will be entered as 4. So again, in part D, we want to find omega at t equals 12 seconds. Once again, we're going to note that when t equals 12 seconds, the time in phase B equals 12 minus the 8 seconds that we spent in phase A, right? So the time in phase B equals 4 seconds. So let's take inventory of what is known for part D. We know the time in phase B is 4 seconds. We know the initial velocity in phase B, but that's about it. We don't know anything else. And by knowing only 2 variables, there's no way to obtain a third variable. And therefore, we're going to have to find some way to find a third variable. So let's take a look at our chart for phase B. Interestingly, the table identifies 3 variables, omega 0, delta theta, and omega. Using these 3 variables, we can determine the angular acceleration in phase B by just putting part D on the side for a moment. Once we find that angular acceleration, we can return to part D and use that angular acceleration as the third variable. So let's pursue that strategy. So again, let's determine the angular acceleration for phase B by using the quantities contained within the chart. So again, the chart contains omega 0, delta theta, and omega, and we would like to use those values to determine alpha. So let's take a look at the rotational motion equations now. Can we use the first equation? Well, let's see. We know the total angular displacement for all of phase B. Omega 0 is known in phase B as well. The overall time was calculated, right? That was 10.8 seconds. Therefore, the only thing that is unknown is alpha, and so the answer is the first equation can be used towards determining alpha. Let's also note that the second equation is useful to us as well. Omega is known, omega 0 is known in phase B, and the time for phase B was also calculated. Therefore, we can use this equation, and since it's a little bit simpler in form, this is the equation that we're going to use towards finding alpha. And so here's the equation. Omega equals omega 0 plus alpha t. And let's keep in mind that we're using the values that are indicated in the table towards finding alpha. So in our chart, omega equals 0. Omega 0 equals 52.35. Plus alpha, and the time that was calculated equals 10.8 seconds. That's the time from phase B. Let's now transfer the 52.35 to the other side. That results in negative 52.35 equals 10.8 times alpha. And if we divide both sides by 10.8, alpha equals negative 4.847. And of course, the units for alpha are radians per second squared. Now that alpha is available to us, we can return to part D. So let's recall that in part D, the time equals 4 seconds. The 4 seconds, of course, is the time that corresponds to an overall time of 12 seconds. Again, let's note that for part D, the time equals 4 seconds. We also know the initial angular velocity in phase B, and that value is 52.35 radians per second. And we just determined alpha, of course. So here are the three variables that we were looking for. We have omega 0, we have t, we have alpha, and we're trying to find omega, which of course refers to the angular velocity of the turntable at a time of 4 seconds. Here are the equations once again. Can we use the first equation? Well, the answer is no, because we don't know the turntable's angular displacement at t equals 4 seconds. Can we use the second equation? Well, it looks like we can. We're trying to find omega. Omega 0 is known. Alpha was just calculated. And of course, the time equals 4 seconds. And so, omega can be found through omega 0 plus alpha t. As we noted, omega 0 equals 52.35. Alpha was just calculated as negative 4.847. And the time that we're spending in phase B equals 4 seconds. The result equals 32.96 radians per second. In part E, we would like to determine the linear velocity of a point on the turntable's rim at t equals 12 seconds. In order to do that, we can use the equation v equals r omega, right? Linear velocity refers to v from one-dimensional motion. We already calculated the angular velocity at t equals 12, so this is the perfect equation for our needs. Once again, the equation looks like this. V equals r omega. The radius was given as 0.3 meters. Omega was just calculated as 32.96. And therefore the velocity equals 9.888 meters per second. Finally, in part F, we would like to determine the turntable's linear acceleration at t equals 5 seconds. Once again, let's note that at t equals 5 seconds, the turntable is still within phase A, right? Because we're spending 8 seconds, here it is again, within phase A. Therefore, at t equals 5, the turntable is within phase A. Let's also note that we're going to rely on this equation, A tangential equals R times alpha, in order to acquire the value for A tangential. The only problem is we have not calculated the angular acceleration within phase A. And so that needs to be done first. Let's once again examine the table. Within our table, under phase A, we can see that omega 0 is known, omega is known, and time is known. And anytime we have three variables that are known, any other variable can be calculated. And so let's use these three variables towards calculating alpha. Now, the first equation will solve for alpha. Delta theta was calculated for phase A, omega 0 was known for phase A, and we also were given the time. The time for phase A was 8 seconds. This equation can be used, but if we can use the second equation, that's the preferred equation because it's a little bit simpler in form. Let's see if it's useful to us. Omega is known in phase A. Omega 0 was 0 in phase A, and the time is known. Time equals 8 seconds. So we prefer to use the second equation. So again, in part F, we would like to find the linear acceleration, which is referred to as the tangential acceleration as well. We abbreviated that as A sub t. And we want to find this acceleration at a time of 5 seconds. As we noted, at t equals 5 seconds, the turntable is in phase A. We're going to use the equation omega equals omega 0 plus alpha t again, and of course we're going to introduce the values that are available to us in the chart from phase A. And so omega equals 52.35, omega 0 equals 0, plus alpha times 8. If we divide both sides by 8, alpha equals 6.544. And the units are radians per second squared, and from that we can determine the value of A tangential through A tangential equals R times alpha, which equals 0.3 times 6.544, and the result is 1.963. And the units, of course, are meters per second squared. And by the way, this A tangential is the same as the acceleration variable within the one-dimensional motion equations. And that completes this lecture.